Hi everybody, and welcome to our video mini lecture on systems and controls. Today's topic is a small topic within ordinary differential equations, and that is dealing with imaginary roots or complex roots more specifically. And as you see, the title here is called Imaginary Roots and Real Solutions. And we're looking at the case of ordinary linear differential equations with constant coefficients when the roots of the characteristic equation are complex. And in fact, we'll find out that, or we'll stipulate, it can be proven mathematically, that if the coefficients of the ordinary differential equation are real, and they are, because those coefficients are things like masses and spring stiffness and that sort of thing, then the roots are either going to be real or complex conjugate pairs. In the case with the complex conjugate pairs, that's where things get confusing, because imaginary numbers don't represent physical quantities, so how does it lead to physical solutions? And so this video kind of just walks through that mathematics, how that all works out. So we'll do it by means of an example. And the example is a simple second order differential equation, second derivative of y plus 2 times the first derivative of y plus 2 times y equals 0, with the initial condition of the function is 0 at time t equal to 0, and its derivative, its first derivative, is equal to 1 at time t equal to 0. And as we know, the first step is to find the characteristic equation that goes along with that, or that corresponds to that differential equation. And it's shown here as p squared plus 2p plus 2 equals 1, and we need to solve for p. And that's straightforward. You go to the quadratic formula that we learned in elementary school and find that the roots are given by that equation you see on the slide, and the roots are indeed complex conjugate pairs. And as you can see, I specifically designed this equation to make the simplest complex conjugate pair possible, minus 1 plus or minus j. So we know that for these linear differential equations, the homogeneous solution will be exponentials of these roots of the characteristic equation times time. So they're complex numbers, they work exactly the same way, and we have here the general form of the homogeneous solution of this differential equation: c1 times the exponential of the first root times time plus c2 times the exponential of the second root times time. So we'll go through a series of steps using various algebraic and trigonometric identities to put this together in a form that makes sense. And of course, we know what the form is. We've studied oscillators in physics and in vibrations and in other classes, circuits class, and we know that this form, this solution has a form of some constant coefficient. I'm calling this a, the amplitude, times an exponential of a negative real number times time, which means it dies out over time, times the sine of the time function at some frequency omega with some phase shift shown here as phi. So this is the general form of the damped vibration, damped oscillation that shows up in second order systems, in underdamped second order systems. So we have a long way to go, I think, you can see, to get to there from our starting point, which is these two exponentials with complex numbers. And I think, we just start working it through. So the first thing we notice is that we have a sum in those exponents, right? 1 plus j, or minus 1 plus j, minus 1 minus j. And you kind of dig back into what we know about exponentials, and we remember that if you have a sum in the exponential, you can factor that out and make it the product of two different exponentials. And so it looks like that. So that e to the minus 1 plus j times t, you can multiply t through, so it's in both of those, and then break them out into two separate exponentials. So that leaves us this coefficient, or this expression we see here, c1 e to the minus t times e to the jt plus c2 e to the minus t e to the minus jt. Pretty straightforward. And then all I did in the next step is pull out that common term e to the minus t. So now our current form of our solution is e to the minus t times these two unknown constants that come from our initial conditions times these two exponentials that both have the imaginary root in there, the square root of minus 1. Okay, the next step is pulling out an identity first formulated by Euler, the famous German mathematician, and he observed that any exponential of a complex number times any real number, so it's exponential of the complex root, square root of minus 1, times a real number, e to the aj, is equal to the cosine of the real number plus j times the sine of the real number. So there's the identity there in the slide. Going back to our expression with these two exponentials, apply Euler's identity to this exponential, apply Euler's identity to this exponential, and you get this term here. And at first it might look like we're heading in the wrong direction. In other words, it's getting more complicated, not less. And we've got still have these j's, so it's not doesn't seem to be heading in the right direction. But bear with me, we've got a few more steps to go, and you'll see where this is all going. First thing I want to do is get rid of these minus signs inside the arguments of these sines and cosines, and we'll just recall two functions or two features, two characteristics of sines and cosines. One is that cosine of minus x equal to cosine of x. That's because cosine's an even function. That's a characteristic of an even function. And you'll recall that sine is an odd function, which means the sine of minus x is equal to minus the sine of x. Okay, so that's where we were before. We apply that even and odd to this, and we get this middle line here. This is looking better. Now we've got all cosines and sines of t. We still have the j's, but now we can factor this along the lines of the trigonometric functions, and we can find we have this kind of an expression: c1 plus c2 times the cosine plus j c1 minus c2 times the sine. So what I'm going to do is I'm going to do a transformation, not a transformation, I'm going to do a substitution. I'm going to say, well, let's define two new constants, one being the sum of these two constants, the original constants, and the other one being the difference times j. So I'm going to define c3, which will be the coefficient of the cosine term, and c4, which will be the coefficient of the sine term. So it includes the difference between these two and that j. And this is the tricky part. This is the part, if you look through the textbooks, it's where it gets a little foggy. Most authors kind of get a little lazy and kind of jump over it a little bit. But it's simply this, that these coefficients C1 and C2 that are originally showing up in our solution are themselves complex conjugate numbers. Okay, they're complex numbers, and they will be a complex conjugate pair. And once we know that, then we can say a few things about it. So here's C3, which is the sum of those two, and all I've did here is just propose the general form of complex numbers, a plus bj. So C1 is some other constant a plus some other constant bj. C2 is a minus bj. Add them up, and you see that we have bj minus bj. They cancel out. The sum of two complex conjugates will always be a real number, and it is 2a. The difference of the real numbers is actually a purely imaginary number, minus 2bj. But remember, we're bringing the j along from the original solution, which means we have j squared. And so C4 also becomes a real number because we've brought in the complex, the imaginary part from those original constants, and then brought in the j from the solution itself. They multiply out and it drops out. And so by that substitution, C3 and C4 now become purely real coefficients, and we've now eliminated the imaginary part of our solution. We went from here, which was just applying Euler's identity and even and odd functions and doing some factoring, to here, substituting new C3 and C4. We just proved they're real numbers, and we now have a completely real solution. So we're well on our way to getting the right answer. And the only thing we'll do here, I kind of left left this gap here to show that there's a little bit of algebra in here, but mostly it's just a trigonometric identity that a sine and cosine of the same argument, same frequency you might say, can be combined into a single sinusoid by the transformation that we have c3 squared plus c4 squared, take its square root, that's the amplitude, and then we have a phase shift, that's the arctan of the ratio between the two. And sure enough, if you say A is equal to that radical and phi is this arctan, we are now right where we wanted to be. The homogeneous solution is equal to A e to the minus t times the sine of t plus phi. So that's really the meat of this. It's not necessarily the most useful piece of information, and you're not going to be seeing it all the time, but I think it's good if we're getting into systems and you're going to be looking at solutions. It's always good to be able to go back to the fundamentals and the basics and see how that all fits together. Okay, so in wrapping this up, let's look at the initial conditions. Let's find the solution. Remember, we had initial conditions to this problem. Y is equal to A times e to the minus t sine of t plus phi. Y dot is given by this expression. I just took the derivative. Remember, it's a product of two functions, so you need the product rule. And so here I took the derivative of e to the minus t, and here I took the derivative of the sine of t plus phi. Apply those initial conditions. H at 0 is equal to 0, so I have a sine of phi equals 0, and y dot is minus a sine phi plus a cosine phi equals 1. So we have two equations, two unknowns, the unknowns being a and phi. It's a little more complicated than your typical exponential kind of differential equation, because one of the unknowns is transcendental. It's inside a transcendental function. So we have to do a little substitution. In fact, it's pretty straightforward, right? If you say, well, a sine of phi is 0, well, that means this term disappears. So we have a cosine of phi equals 1. That's still not exactly enough to give you all the details you need, because you still have two equations, but you just keep moving in that direction. Just do the algebra, and you can find that the correct answer here is a equals 1 and phi is equal to 0. So it's those are the two constants, and I just went into MATLAB and did a real quick computation to graph what that solution looks like over time. So you see it starts at 0, it rises fairly rapidly, peaks out here at about 3/4 of a second, falls down just around 3 1/4 seconds, it goes back below 0, and you see it rising up again. And if I were to continue to plot it, you'd see it now asymptotically approach 0, approach its steady state value. So we can see one of the initial conditions is easily met. The other initial condition is a little harder to see on this plot, because it's the derivative, right? It's the slope. But what the initial condition said was that the derivative of our function y here is equal to 1 at time t equal to 0, which means if we drew a line that was tangent to this function at time t equal to 0 and extrapolated out, it would go up along here, and if its slope should be 1, and if its slope is 1, that means it should hit a y value of 1 at the same time it hits an x value of 1. So this graph is hard to see because I cut it off, so it's only about 0.35, but it looks like it might possibly be moving in the right direction. So to check on that, I went back into MATLAB and I had to draw that line, the line that went from 0 here, 0, 0 to 1, 1. So it's a line of slope 1 with the intersection at the origin, and if we got the initial condition right, that line should be perfectly tangent to this solution at time t equal to 0. And sure enough, that's the green line here. And I'm now looking at a different range. I kind of zoomed up on just this part of it. So you can see here's time 1 second, here's the amplitude of 1, there's the line going right through it, and sure enough, this is the solution. Like I said, I scaled it differently. I kind of zoomed in, so it looks different, but it's the same solution. See, it rises up to a little over 0.3 Here at 3/4 of a second, same one. And sure enough, at time t equal to 0, that green line sure looks tangent to the blue line, which is the solution. So we have some pretty good confidence in that. So that's what I wanted to talk about here. I wanted you to get a sense of this. When you're working the homeworks, you're probably going to want to see that. It'll be the easiest way to work through those problems. And that is it. Thanks.